Hi, my name's Andrew McLaren. We're going to go over Le Chatelier's principle, talking about it generally, and then looking at some example problems and working through that. This can be fairly straightforward sometimes and a lot more tricky other times. And it's because that there's situations where you're kind of changing Q and other times where you're actually changing K itself. And that can be a bit unclear as to what's going on there, but we're going to start with just defining what it means for something to be going to the right. When something is shifting, right, that means that you're making more products. So you need to make more products when it shifts to the right. When it shifts to the left, that means that you're making more reactants. But these things are responses. So when we're talking about a shift to the left or the right, this is some sort of effect that is due to some sort of cause. So oftentimes you do something, like there's a cause that you're like that's causing some sort of response, but you're going to kind of move things in one way, and then the reaction responds by moving things back over in a different way. So the easiest ones to understand is, like, let's say that K is constant and you change Q. This is going to be things like when you're just adding or taking away some reactant from the reaction. So if we have like in this question set here, we've got a number of problems here. Some of them are a bit more straightforward and probably easier for you, and some are going to be a little bit harder. So if we look at question 3 here, they're saying that say that we're adding this NO2. So that NO2 right there is being added, and in that case, the Q is being increased, like the initial amount of this concentration. If you were to think about this in terms of like an ice chart, if you were doing like initial change and equilibrium, you can oftentimes think about Q as being related to your initial, and then K equilibrium is being related to the E or the end point of this ice table. So if we did an ice table here, what you're essentially saying is, like, I'm going to make a bunch of product, and if we think about that, then I've got too much product. So in response to that, you're going to need to take some of that product away and make more reactant. So this is said to shift to the left. Um, if you've made Q be too big, we got to bring that down so that it's more like K equilibrium. So if Q is too big, there's going to be some sort of, in terms of the reactants and products, you gotta then end up having a change in response. This is that shift where you're taking away some value away from product and you're adding it to the reactant. In this case, we've got 2 of these being consumed for every one that's being made there, so you need to take 2x away for every x that you're making of the reactants as a response to that cause, or um, what we did. So if we then look at something where pressure is changed, K equilibrium is still the same, but we're going to then think about that in terms of like the pressure and the volume changing and causing Q to actually change. So if you think about PV is equal to PV, like P1 V1 is equal to P2 V2, when you lower this pressure, then like the volume is getting bigger. So let's say that we're looking at this reaction, and I'm going to just do very simple numbers to help demonstrate this point. Let's say this reaction's Q value was equal to just 1. And remember, K as well as Q are related to products over reactants. So we've got the products, and it should be squared because it's up to the second power with that coefficient of 2 that we're seeing in it. So if I think about this, you've got some sort of number that's being squared all over some other number. We're just going to use some very simple numbers to demonstrate a point here. So let's say that it was at 1 atmosphere for both of these. And that gives you that K of 1. Let's say that by changing the volume, let's say you've lowered the pressure, it's increased that volume. So you're at some sort of Q now that's been changed in response, that is changing by you doing something. So there's some sort of cause that's happening now. So you've got an increase in volume and decrease in pressure. So let's say that this is maybe like 0.5 atmospheres now for both of these things the moment that you do the change. But if you do a little mental math here, you should see that this is coming out as 0.25 over 0.5. So math-wise, this is a Q value that's too small. If you have things where there's more products than reactants in terms of the gases or the ions there in concentration, that's going to, square out differently than if you've got more reactants. So this is going to depend on the side that has more or less molecules of the things that are competing for space on the two sides. So this will, like, lowering the pressure is going to shift this either left or right depending on if you've got a side that's being kind of squeezed into more or less moles on the two sides of the reactant and product. So if we look back at this question here, what we're basically saying is if I'm lowering the pressure, there's more space available for more things, and so I'm going to need to end up shifting this to make more product. Because my Q is smaller than my K, you can imagine that in response to that, so we've done some sort of cause, which I've done in pink in response to that, because Q is equal to the products over the reactants. We're going to need to make this number bigger, and to make that number bigger, we need more products and less reactants. So there's going to be this response to our change of pressure by making there be a shifting to the right, or a shifting to making more products there. So it's a bit weird, but we've essentially changed Q in a different way when we're messing with pressure, as opposed to just directly changing the concentrations of the two things. I will highlight a pressure problem that goes the other way in a little while at the end of the video, but for now we're going to move on to like temperature. So if you think about temperature, this change in H value right here is a positive number, and how temperature is going to get shifted will be different for exothermic and endothermic reactions. If you think about an exothermic reaction, that gives off heat, so energy would be a product, but in this case you can think of energy as a sort of reactant. So if we look at reactants and think of energy as that reactant, when you have a temperature being increased, so the temperature is being raised, that causes the amount of energy to be bigger, and that's like having a reactant that's bigger. So that's the cause, and then the effect of that is that it should shift this to the right. So it's kind of like you have too much reactants in this situation, but you could imagine if the energy was on the other side of the equation, we would have the opposite effect here, shifting to the left. So if we're talking about exothermic, it shifts it the other way. So we end up having this shift to the right. This is some work that I had from some student. This is not necessarily correct. The answer C right here is actually incorrect. So we see a shift that goes to the right when we're increasing that energy there. It's a bit weird, but essentially you can look at this with like Gibbs free energy as well and talk about the relationship with Gibbs free energy. But I'm going to hold off on that because it gets pretty advanced and complicated. But the big picture is that entropy is not going to have an effect on equilibrium that's different at different temperatures. It's really the enthalpy and the enthalpy change that's going to have more or less of an effect at different temperatures, which kind of makes sense because if it's warmer, you've got more enthalpy around you. So that effect might be a bit different than if you didn't have as much. So in this type of situation, this is the situation where K is being shifted. So K is changed by temperature. So the exact K equilibrium is changed by the temperature. So if we had these things being equal to 1 and K was equal to 1, then you could say that K is now maybe equal to 10, just to make our math easy. And our Q value is what it was. Let's say it was at 1. And previously, K was equal to 1. So like these two things were equal. But now in this situation, you can think like, well, to get to being K equilibrium, I've got to make this be bigger. So I've got to make more product and less reactant. And so we're seeing that shift to making more product and less reactant by adding this energy in for the endothermic reaction. But it would be opposite for exothermic. Catalysts, these things, they're going to be not really affecting your equilibrium position that much because a catalyst is going to cause your reactants and products to have like different activation energy. So if I add a catalyst to a reaction, it doesn't change the change in H, it just changes the enthalpy for going up to the activation energy. But the enthalpy change of the reaction is still the same for those two situations. It just is going to allow you to get to that equilibrium faster. So these have the same K equilibrium, but catalyst helps you get there faster. So you're not changing Q equilibrium or Q or K and those different values in these types of problems. When you add a catalyst, it just goes so much faster. You might actually see a change where something might take years or even thousands of years. You could have it happen in a couple hours or a couple seconds with the right catalyst. So if we're trying to think about all these different things, we're trying to get this thing to have the K equilibrium change. That's really only due to like temperature. So in the big picture on the 7 here, your K equilibrium can only be changed by either adding energy into the system or taking it away. So we can increase the temperature or decrease the temperature. And that's effectively our two options. If we want to think about this reaction, it was endothermic. And as a result, if you increase the amount of energy, it shifts it to the right. And if you want to decrease energy, it shifts it to the left. In other words, we need to be putting this reaction on ice because that's going to lower the K equilibrium for this type of problem. But that would have the opposite effect for an exothermic reaction. Cooling it down is like saying I've got less product now and I need to make more product for an exothermic. We're just talking about endothermic in this earlier problem. If we then look at this, I really wanted to focus for this problem on the pressure change. So coming back to that, because I think the temperature and pressure changes are probably the trickier ones here for people. So if we're focusing in on this pressure change of the system, in this problem, we're seeing, let's do another K equilibrium that's equal to 1. But think about for that product, see, I just did it wrong. That product over the reactant. And we can think about, in this case, I've got 1, 2, 3 things that are reactants, so I'm just gonna put that up to the third power, and then 1, 2, 3, 4, 5, 5 things as products, just making this as simple as possible, that and say that maybe these are all 1 atmosphere. And then by decreasing the pressure, we're going to have a Q that's equal to a like the 0.5, or an increase in pressure. Let's say maybe it's an increase and we're going up to like 2 atmospheres for everything. So we're increasing that pressure. As you can see, there's going to be a Q that's bigger than 1 in this situation. And the exact number would be like 2 up to, was at the second power, so it's like 4. In that situation, we need to shift things appropriately. So we've caused some sort of change. There's a cause of us changing the pressure, and the reaction is going to shift appropriately, saying like, oh, well, I've got too much product here. I need to make more reactant. So that would then cause it to shift to the left right here. I'm going to leave you with a challenge question where you're trying to figure out which one of these answers is correct. Go ahead and put it as a comment in the comment section of the video. I did need to add in the change in H value here because this question, without that information, you can't think about the temperature change and how that affects the shifting to the left or the right. Okay, I think that's just about everything for Le Chatelier's principle. Just be patient with yourself. You're either changing K or Q directly, and then the reaction needs to respond to that, or it needs to have a shift in response to what you've done to reestablish that equilibrium. Either it's coming back to the same K equilibrium, or you've changed K equilibrium and now it needs to get there, which is with temperature. That's the only one that really changes the K equilibrium. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there. And we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.